In this video, going to trace through the Quicksort implementation that we will be using in our course. Now, you might see different implementations of Quicksort, but they all follow the same general algorithm, this idea of partitioning the array and making sure that that element in the middle, the pivot, is in its proper place, and that everything to the left is smaller than, everything to the right is greater than, and then recursively doing that same process on the left and the right. So that's the same algorithm that all of the Quicksort implementations will use. Now, different implementations you look at might work a little bit differently in which direction they scan from or how they choose the pivot value, things like that. As I mentioned in the previous video, the choice of a pivot value can really affect your efficiency, and that's a very, very big topic to think about. As I mentioned, it's one that people write dissertations on, so it's not one we're going to focus a lot on, but just be aware that you might see a different implementation of Quicksort. It might look a little different than this, but it's going to follow that same algorithm. So we're going to use this version just because I want to trace through something and to give you a concrete example of what's happening while we're looking at the code. But again, just keep that in mind. So the code that we are using does have a couple of efficiencies. The first thing is when we get down to a very small data set, it just calls insertion sort. So this is our Quicksort method. We invoke it with just sending in our array, and then much like the other methods that we've looked at that use recursion, it has a helper method, and the helper method is actually the one that's recursive. So we're going to call the Quicksort helper method, passing in the array and then the first and last indices, so 0 and array.length -1. So this is our helper method. The helper method is going to, again, check and see the size of this array, and if it's a small enough size, so the size set here is 5, you might see it 10, or you might see that number a little bit different, it's just going to use insertion sort. We know that those slower sorts like insertion sort are actually fine if it's a small enough data set. So we don't have to worry about any efficiency hit there. So down here we have a helper method that we're going to use, insertion sort, and this is just insertion sort, that's all it is. And we're only going to call this again if we get down to that small size. Now in the trace today, I'm going to ignore that because I don't want to have to trace a crazy large array. It'll be hard to keep track of. So I'm going to pretend that we're not using that modification, that we're not doing any insertion sort, just so that we can trace a normal handable size array, an array that's small enough that we can visualize it on the screen. But that is one efficiency that's in this version. The other efficiency is in the partition method with the sorting of first, middle, last. We'll take a look at that when we get there. But here we are in Quicksort. So again, if it's a very small array that we're getting, we're going to just use insertion sort. But otherwise, we're going to go into the main algorithm part of Quicksort, which is where we first call the partition method. So although this is the Quicksort algorithm, Quicksort method, partition is really the workhorse of how this algorithm works. The partition method is the one that finds that pivot value and then shuffles everything so that everything to the left is smaller than the pivot and everything to the right is greater than the pivot. Now remember that it doesn't mean the left and right sides are sorted. It just means that that pivot is in its proper position. Again, meaning everything to the left is smaller than the pivot, everything to the right is greater than the pivot. And if we knew that, right, if we knew that, hey, this is the index at which everything to the left is smaller, then we have our pivot at some pivot index, and then everything to the right is greater, then we could make this a recursive solution and we'd say, okay, I solved a small part of the problem. I put the pivot, one element, in its right place. I put the pivot in its pivot index. That's where it's going to go when everything's all sorted. We know that because everything to the left is smaller, everything to the right is bigger, so that pivot must be in its proper place. So that's the small part we solve right now by calling partition. Then recursively, we'll just say, okay, let's solve the rest later. Let's call this same thing we just did, this Quicksort helper method, and let's send in the left side. So the indices there are first and one to the left of the pivot index, because that's the left side of the array that we know all those values are smaller than pivot, but they're not sorted, so we need to repeat the process there. Then we'll make a second recursive call to the right-hand side, and we'll say, okay, the first index of the right hand side is pivot +1, pivot index +1, because we know, again, pivot's already done, and we'll go up to last. So we're going to say, okay, we know all those values are bigger than pivot, but they still need to be sorted. So let's recursively sort that part of the array. And then we just continue on. So we, again, would recursively come into this method with the left side, partition that, and then recursively call with the left and the right of the left side. Similarly, we come into the quicksort with the right side, partition that, and then recursively call the left and right of the right-hand side. So we kind of, partition and partition and partition, smaller and smaller down, until at some point we're going to pass in an array that's smaller than our minimum size, at which point we're not going to make a recursive call anymore. We're just going to use insertion sort. Okay, so that's kind of generally how quicksort works. It's the partition, like I said, that's the workhorse. So this is sort of the magic part, right? We were to say, well, if I magically had some way to know that the element in this index, in the pivot index, was in its proper spot, and that everything to the left was smaller and everything to the right was greater, well, then I could just go ahead with these recursive calls and my whole thing would be sorted. So make sure you understand that general idea before we move on to looking at how partition actually works, because again, partition could be implemented slightly different ways with slightly different improvements, but it's important to understand this general idea of how quicksort works, meaning I partition the array such that the pivot's in its right spot, and then I recursively, again, sort the left part and the right part, which those recursive calls are going to use partition on the left and partition on the right, and so on and so on and so on. So let's now look at how partition actually works. So again, partition's job is to take one element, the pivot, and put it in its proper place, the pivot index. And then we send back that pivot index to tell Quicksort, okay, this is the index of the element that's in its final and proper place. Now you recursively do the rest. Okay, so let's look at partition. So here we just are passing in the array and the first and last index. We find the middle, and then here's one of our efficiencies, sort first, middle, last. This efficiency is not built into the quicksort algorithm. You can run quicksort without this and it's still going to work just fine. But this is one of the efficiencies that helps move us towards that average case of n log n and helps keep us away from that worst case of n squared. So this is one of those modifications. If we go down to the sort first, middle, last method, does something very easy. It just takes it just takes three elements in the array, the first, the middle, and the last, and it just sorts those three elements. And it just does that by brute comparison, okay? So we have another helper method here, swap. All that our swap does is it takes the array and two indices, I and j, and it swaps the values at those indices. So it says, if you give me 2 and 5, I'm going to take the array, the value at position 2, and I'm going to put it into index 5, and I'm going to take what used to be in index 5, and I'm going to put that value into index 2. So it's a pretty simple swap, traditional swap method. It just swaps two values. So back into sort first, middle, and last, all we do is we say, okay, if the value at first is bigger than the value in the middle, swap them. If the value in the middle is bigger than the value in last, swap those values. And then we need to go back and again compare first to middle, since we've swapped last into middle. And if first is bigger than that new middle, again, swap them. So at the end of this call to sort first, middle, and last, three elements in the array will be sorted relative to each other. So out of those three values, the smallest of those three values will be in the position of first, the largest of those three values will be in the position of last, and the middle of those three values will be in the position of mid. So that's all it does. It just sorts those three values relative to each other. And again, the only point of this is it's just an efficiency to help keep us away from that worst case n squared. So that's pretty straightforward. That's all it does. And we do that right when we get into partition. Okay, so we sort those three values relative to each other. Then what we do is we swap the element in the mid position with the element in last minus 1. Okay, essentially what we're doing here is we're trying to make the pivot be at the very least not the smallest or largest value in that part of the array. So if we can make sure that the pivot isn't, again, on some extreme, smallest or largest, it's going to help keep us away from that n squared. So that's all the point of this is. Once we make that swap, we then say, okay, well, that is the pivot index. Our pivot index is going to be last minus 1. Last minus 1 now holds this, what used to be that middle value. What was that middle value of those three? Okay, so that's our pivot index. Let's get the pivot value, which is just the array at that index. And now we're going to start this left and right scan of looking for elements that are bigger than the pivot and moving them to the right, and looking for elements that are smaller than the pivot and moving them to the left. So we're going to have an index that we're going to come in from the left-hand side. That's going to start at first plus 1. We don't need to look at first because we already know it's smaller because of that call to sort first, middle, last. And we don't need to look at last because we already know that it's bigger because of that call to sort first, middle, last. And last minus 1 holds the pivot, so we also don't need to look at that. So we're going to start at first plus 1 and last minus 2. And then we're just going to enter this loop and say, okay, as long as the values, starting with the index from the left, starting over the left-hand side of the array, as long as the value I'm at is smaller than the pivot, just keep incrementing that index. Just keep moving it to the right, to the right, to the right. As soon as I hit a value that's greater than or equal to the pivot, stop. Exit this loop. I come into another loop, and now I'm moving from the right-hand side, and I'm looking at the values, and I'm saying as long as I see a value that's bigger than the pivot, keep moving left, keep decrementing, left, left, left. As soon as I find a value that's equal to or less than the pivot, stop and exit that while loop. Now here we have an assert statement. All this is doing is it's just telling us what we already know to be true, that whenever we exited these while loops, we know that that index from the left is pointing at some value greater than or equal to the pivot, because that's what popped us out of that loop, and that the index from the right is pointing to some value less than or equal to the pivot. Again, that's what exited us out of that second loop. And so now we're going to come in and we're going to say, okay, well, as long as that left index is smaller than the right index, let's swap those two values. Because remember, the left index is pointing to something bigger than the pivot. The right index is pointing to something smaller than the pivot, so we want to swap them. So that now the smaller value, the value smaller than the pivot's on the left, value bigger than the pivot's on the right, and then we just increment those and decrement those indices one more time and loop back around and repeat the same process. Keep moving in from the left looking for something bigger. Keep moving in from the right looking for something smaller. When we find those values, swap them and then keep looking. And we do that until, we'll set this to done, once the indices cross over. So we only ever do a swap if the left index is less than the right index, and then we'll swap. If the indices have crossed over, then we're done. So we'll come back around and the while loop will exit. At that point, we're going to swap the pivot into its proper position, and then we return that index. All right, so let's actually trace through this with an example. I think that can be helpful. A couple of things to be really careful about when you're looking at partition is keeping in mind the difference between the index and the value, right? So we're going to be moving indices, but anytime we're making a decision about whether to swap or where an element should go, we're going to look at the value, not the index. So just kind of keep that in mind. That's sort of one place to make kind of an easy mistake there, is kind of separating this index from value. So let's take a look. We are going to walk through partition. Well, we'll start with Quicksort, but really we're just going to look at partition with this array here. So this is an array with 13 elements. You can see it's obviously unsorted. So we've got our indexes from 0 to 12, and here are our elements. So if we were to call Quicksort, we would come in here, and in this case, we actually are longer than our minimum size, so we really would go into the else. And here we're going to say, okay, give me the pivot index. So we're going to say, hey, partition method, I'm going to wait for the pivot index. And again, what the pivot index is it's the index of the element that's in its proper and final place. So this is what we're waiting for. Okay, so this gets paused and we call partition. Going into partition, we send in this array and we send in first index. I suppose they just call it first, which is 0. Last, which in our case is 12, and that's what gets passed into partition. Okay, now again, these are the indices. So first index is 0, last index is 12. Hopefully my diagram here hasn't made it more confusing to keep those track, because I am pointing at the value here. But remember, this is an index, so it's going to be 12 and the 0. That's the first and last indices. So we come into partition and we just calculate mid, first plus last divided by 2, which in our case is going to be 6. So mid is going to, this is an index again, it's going to point to the 6. And then we go down to this sort first, middle, and last. So when we sort first, middle, and last, what we're saying is the array at position first, that's 16, greater than the array at position mid, the 2? Well, yes, it is. So let's swap them. So let's swap the 16 and the 2. Now, is the array at position mid, the 16, greater than the array at the position last? Yes, it is. So let's swap them. 8 goes here, 16 goes here. And now, of course, we have to do one final comparison. We have to go back and again compare first and mid. So is the value at first greater than the value at mid, this time it's not, so we don't do any swaps. And now this method is done. And again, what this method has done is it's taken these three values, the 2, the 8, and the 6, and it's just sorted them relative to each other. It's not saying anything about where they're going to go in the ultimate placement of this array. It's just saying that compared to each other, those three values are sorted, 2, then 8, then 6. That's all this method does. Okay. Now, I did want to mention the two things to keep in mind. I already mentioned the idea about indices versus values. The other reminder I just wanted to make is this idea about compare to. So because we're using comparable elements, we're using the compare to method. We're not just using less than or greater than or equal to. So remember that compare to, if it returns a positive number, that means that the invoking object is bigger than the parameter object. So in this case, array first greater than 0 means that array first is bigger than array mid. If it were less than 0, that would mean that the invoking object is less than the parameter. And if it's 0, it means they're equal. So just keep those rules of compare to in mind as well. All right, so that's sort first, middle, last. And now we have a call to swapping the values at mid and last minus 1. So mid is 8. Last minus 1 is 11, so that's the value of 7. So we're going to swap these. We're just going to put the 8 in last minus 1, and we're going to put the 7 in position mid, and that's this call here. That's the swap. And now we know that our pivot index is last minus 1, so that's here. So this is our pivot index. This 8 is going to be our pivot value. So that's our pivot. The 8 is our pivot. Okay. Pivot index is 11, but our pivot value is 8. Now, the reason, again, we did this sort first, middle, last was because we wanted our pivot to be not the largest element in the array and not the smallest element in the array. And we don't know that 16 is the largest or that 2 is the smallest. In this case, 2 is not the smallest, but we know at the very least that there's at least one element bigger than 8 and one element smaller than 8. And just knowing that our pivot is at the very least not as a baseline is not the greatest or the smallest element in the whole set will help keep us away from that n squared. Okay. We also now don't need to look at the 16 and the 2 in our partition anymore because we know 16 is greater than the pivot and we know 2 is smaller than the pivot. Okay. So that's our pivot index, and now our pivot is the value of 8. So now we can set up our index from the left, which is going to be first plus 1. So that's going to be index 1 here, value of 9. And our index from the right is last minus 2, which is going to be here, the 10. The index value of 13, index of 10. Now, from this point forward, I don't need first, mid, and last. So I'm just going to hide them so that they don't confuse us in this trace. So I'm just going to get them out of the way here. Okay, so just we don't have to focus from them. And again, first, our index from the right is going to be 10. Index from the left is going to be 1. And now we're going to enter our loop. So done is false, not done is true. So we come in and we say, okay, we're going to look at the value and index from the left. And if it's smaller than the pivot, if comparing to returns a negative number, I'm going to move that index to the left forward. I'm going to increment it. So is the value and index on the left is 1? Is that smaller than 8? No, it's not. So I just skip this while loop entirely. Now I'll come into the next loop and say, okay, is the value at index to the right, 13, is that greater than the pivot? Compared to returns a number greater than 0. Well, yes, it is. So I'm going to enter this loop and I'm going to say, okay, index from the right, let's move it down 1. So index to the right gets bumped down to here. And then I loop back around. Okay, is the value at index from the right, the value of 6, is that greater than my pivot, the value of 8? No, it's not. So I'm done with this loop. So now I've exited both of those while loops. And here I come to my assert. Again, don't worry about the syntax of an assert. An assert is just a way to state what you already know to be true. It's kind of a check on yourself. So is it true that the value at index from the left, 9, is greater than or equal to the pivot? Yes. Is it true that the value at index from the right, 6, is less than or equal to the pivot? Yes. So we're good to go. So now we get down to our conditional. Is the index from the left, 1, less than the index from the right, 9? Yes. So we're going to enter this conditional. This is one place where we're again comparing the indices, not the values. The index on the left is less than the index from the right, so we're going to enter. And we're going to swap those two values. The value and index from the left, the 9, we're going to swap with the value and index from the right, the 6. So we're going to swap them. And we're doing that because we know the 6 is smaller than the pivot, so we want it over towards the left. We know the 9 is bigger than the pivot, so we want it over towards the right. So we're going to swap them. Now we've also already looked at these elements, so we're again going to move our indexes. We're going to move our index from the left forward 1 and our index from the right back 1 or down 1. And that's the end of our while loop. We didn't reset done, so we're going to go back around. Done is still false, so we're going to come in again. And we're going to do the same process of scanning from the left, scanning from the right. When we find two elements that meet our criteria, we'll swap them. So we'll hit this first while loop, and we'll say, is the value at index from the left, that's the value 11, is it less than the pivot, the pivot value? No, it's not. So we don't enter that loop at all. We come to our next loop and we say, okay, is the value at index from the right 5? Is it greater than the pivot? No. So we also don't enter that loop. So now we've got through both of those loops. We come down to our assert. This is just our reality check on ourselves. All right, that keeps jumping. And we say, okay, is the value at index on the left 11? Is it greater than or equal to 8? Yes, it is. Is the value at index on the right 5? Is it less than or equal to 8? Yes, it is. So we're good to go. We come into our conditional. Is index from left is 2 less than 8? Yes, it is. So we come into our conditional and we do a swap. We swap the value in index from the left with the value in index from the right. Again, moving the smaller values down to the left, the larger values up to the right. And then again, because we've already evaluated those two values, we're going to increment left up 1 and right down 1. Then we loop back around. Done is still false, so we come into the outer loop there, and we say, okay, is this value at index on the left, the value of 3, is that less than the pivot? Yes, it is. So we enter this while loop, and we move index to the left, index on the left, up 1. Then we say, we loop back around. Okay, is the value at index on the left 14? Is it less than the pivot? No, it's not. So we exit this loop. Enter into the next loop. Is the value at index from the right 4? Is it greater than 8? No, it's not. So we skip that loop. Let's get a reality check on ourselves here. Is the value at index on the left 14 greater than or equal to 8? Yes, it is. Is the value at the index on the right 4 less than or equal to 8? Yes, it is. So we're good to go. Is the index of 4 less than the index of 7? Is 4 less than 7? Yes, it is. So we enter our if, and we swap these values. We swap the 14 with the 4. And then again, we increment index from the left up 1. I'm just going to have to put it down here a little because these two pictures will get joined. And we move index from the right down 1. Come back around to our outer loop. Done is still false, so we enter the while not done. We check our values. Is the value at index from the left, that's the 1, is it less than our pivot, 8? Yes, it is. So we move index from the left forward. It's now pointing at the same place as index from the right, the index 6, which is a value of 7. We loop back around. Is the value at index from the left, the 7, is that less than the pivot? Yes, it is. So we move it up again. So now here our index from the left is pointing at 7, the value of 4. Is our value of, 14. Is our value of 14 less than the pivot? It's not. So we exit that loop. We come to our next nested loop. Is the value at index from the right 7 greater than the pivot 8? No, it's not. So we're done. Okay, let's get to our reality check. Our assertion statement here is the value at index from the left 14 greater than or equal to 8? It is. Is the value at index from the right 7 less than or equal to 8? It is. So we're good. Then we enter into the if. Is the index from the left, the index of 7, is that less than the index from the right, the index of 6? Well, no, it's not. So now the indices have crossed over each other, and so now we're done. So we go into the else. We set done to true. When we come back around to our while loop, it'll fail and we'll exit. Okay, so we stop scanning when the indices cross over. Now we get down to the next swap outside the loop, and we're going to swap that pivot index, which is our index 11, our value of 8. We're going to swap that value with our index from the left, which was the 14. So we swap the 14 with the 8. And then we say, okay, pivot index now gets our index from the left, which is 7. Let me move this out of the way so they don't get joined together. And that's what we return. We return that pivot index, which is 7. So back in Quicksort, the pivot index returned to us from this whole call to partition is 7. And what does that mean? It means that the element in index 7, this 8, everything to the left is smaller than 8. We can see that that's true. 2, 6, 5, 3, 4, 1, 7. Those are all smaller than 8. And everything to the right of this index is greater than 8. 11, 9, 13, 14, 16. That's also true. Now again, it doesn't mean that these values are sorted. Clearly 2, 6, 5, 3, 4, 1, 7 is not sorted. 11, 9, 13, 14, 16 also not sorted. That's not what partition does. All it does is that it picks one value and it makes sure that one value is in its final place. So when this whole array is sorted, the value of 8 is going to be in index 7. It's going to be in that spot. And that's what the pivot index does. That's what the partition method rather does. And that's what pivot index indicates. It means that one value, that pivot, is in its final spot, the pivot index. So now what we would do is we would move on to our next recursive calls. And let's bring back up our first and last that we kind of hid before. Bring those back up for Quicksort. So this was our first and last, and now we're going to have two recursive calls. The first one is going to call Quicksort again with first, and now for the pivot, the value of last, it's going to use pivot -1. So it's going to use this here. And we're going to make a second recursive call for the value of first. It's going to use the index plus pivot index +1. So here. So we're essentially now going to sort, we're going to quicksort just these 5 values and just these 7 values. But we ignore 8. 8 is done. It's sorted. It's good to go. 8 is in its final spot. Now we need to recursively call quicksort with the left side and the right side. So in our case, if we were to do that, both of them would be insertion sorted because they're both, oh wait, actually, what do we have? Min size is 5. So actually, they would, because they're, yeah, they're both, they would both be, we would go into the else on both of them. If our min size was 10, for example, which is also a common minimum size, then these would both be insertion sorted. But for 5, we actually would go through another pass of quicksort. And I am going to just quickly trace through one more call to partition with the left and the right. So we'll again pretend we're coming in here with our now first index and last index being 0 and 6. 6 minus 0 plus 1 is 7. That's greater than or equal to the minimum size. So we'll come into our else and we'll say, okay, let's call partition with 0 and 6 as our first and last. So I'm going to walk through this one a little bit quicker this time. So we'll come into partition. Again, we're just going to look at this left-hand side right now. We will calculate the mid as 3, 0 plus 6 divided by 2, and we'll call that call to sort first, middle, and last, which in this case is the 2, the 3, and the 7. After that call, nothing is actually going to be changed, right? Because 2, 3, and 7 relative to each other are already sorted. What I actually want to do, because I'm going to just hide this other part of the array that we're not dealing with. I'm just going to cover it up so we don't get confused, and because we're again just focusing on one call to partition at a time. So this is our array that we're dealing with. Okay, so again, sort first, middle, and last. 2, 3, and 7 are all in their proper relative positions. So now we swap the value at mid, which is the 3, in with the value at last -1, which is the 1. So the 3 and the 1 swap, and now that is our pivot index. Sorry. There. Come on, pivot index. Let's again cover this all up. Okay, so that's our pivot index. It's going to be, the index is 5. Our new pivot value is going to be 3. And now we can say our index from the left is first plus 1. So index 1. Ignore first for a little while. And our index from the right, with mid for a while, is going to be last -2. So index 4. And now we can enter into our loop. Okay, again, keeping in mind that our pivot value is 3. So we're going to say, okay, as long as the value and index from the left is less than the pivot, we're going to move that forward. So is 6 less than the pivot? It's not. So we skip this loop. As long as the value from the right is greater than the pivot, we're going to move down from the right. Is 4 greater than 3? It's not. So we check ourselves. Is 6 greater than or equal to 3? Yes. Is 4 less than, oops, sorry, I made a mistake there. Okay, going back up to that while loop. Is 4 greater than 3? Why, yes, it is. That was my mistake there. So we move index from the right down 1. Okay, so now, all right, when it gets a little crowded in here, it gets harder to move these things. Okay, so now index from the right is decremented 1, and now we say is 1 greater than 3, and now it's not. So now we exit this loop, and we again, so that's why we have that good check on ourselves. Is 6 greater than or equal to 3? It is. Is 1 less than or equal to 3? It is. So now we enter our conditional. Is the index of 1 less than the index of 3? It is. So we're going to swap them. We're going to swap the 6 and the 1. And then we're going to advance these. So index from the left moves forward 1. Index from the right moves left 1, decremented 1. And we come back around and we say, okay, is the value of index from the left less than the pivot? Is 5 less than 3? No. And then we say here is the value of index from the right 5 greater than the pivot? It is. So we move index from the right down. Is the value of index from the right 1 greater than the pivot? It's not. So we're done. And let's check ourselves. Is the index from the left value 5 greater than or equal to the pivot? Yes. Index from right value 1 less than or equal to the pivot? Yes. So we get to our conditional. Is the index from the left, the index of 2, is that less than the index of 1? It's not. So we're done. We exit the outer loop. We come here and we're going to swap the index from the left value with our pivot value. Essentially, we're now putting the pivot into place. And then we would return that. So now back in this call to Quicksort, our pivot index would be 2. And you can see now again that the 3 is in its proper place. Everything to the left of the 3 is smaller. Everything to the right of the 3 is greater. And we would now recursively call Quicksort with this just 2-element array and this 4-element array. And the whole thing would repeat. Okay. So looking again, our last trace here. At the right-hand side that we got from our previous call to partition. So let's bring this over here. Let's hide this part that we already looked at. And now this was the call where we are having first index is 8 and last index is 12. So this is our call to partition from the right-hand side. So we come in here. Our mid is going to be 10. And we're going to do a sort first, middle, last of 11, 13, and 16. Again, in this case, that's the 3 of them are already relatively sorted to each other. So now we're going to swap mid, which is the 13, with last minus 1, which is the 14. And 13 is now going to be our pivot. It's going to get pretty crowded in here. Okay, but now we can have our index from the left is going to be come on, index from the left is going to be first plus 1, so it's going to be 9. Index from the right is going to be 12, last minus 2, 12 minus 2, which is going to be the 10. So they're pretty close to each other just to already begin. And we're going to start looping. So is the value at index from the left smaller than the pivot? Is 9 less than 13? Yes, it is. So index from the left moves up. Is 14 less than 13? It's not. So that first loop is done. Now looking at the right, is the value at index from the right, is the 14 greater than 13? It is. So index from the right moves down. We try again. Is the value at index from the right 9 greater than 13? It's not, so we exit. Let's check ourselves. Is 14 greater than or equal to 13? Yes. Is 9 less than or equal to 13? Yes. And so now we do our conditional. Is the index from the left 10 less than the index from the right 9? No, it's not. So we're actually just done in this case. And now we swap the pivot into place. So we swap the pivot with the index from the left, and then we would return that pivot index, which I never even pulled up here, which in this case would be 10. And again, we know now that the pivot is in its proper place. Everything to the right in this little subarray is greater. Everything to the left is smaller. If we look back at our original array, the whole thing, the 3, the 8, and the 13 are all in their proper position. The rest of the numbers aren't sorted yet, but those 3 elements are all in the proper place. And that's how Quicksort works. It just repeatedly partitions into smaller and smaller subarrays until you get to a super small subarray like of this one of size 2, and then you just insertion sort them. And then everything will eventually be in sorted order because of those repeated calls. So that is your trace of Quicksort. Keep in mind again this difference between comparing values and comparing indices. This is the spot here where the index is compared. Other places we're comparing the values. And then also just keep in mind those rules for compare to. When the value is negative, that first invoking one is smaller. When the value is positive, that first invoking one is bigger.